Ladies and gentlemen. Also on behalf of my colleagues Carl and Nicola, I'm warmly welcoming you to my today's talk about how to predict delays in disrupted railway networks using a graph neural network model. My name is Szymula. I'm a researcher at Technische Universitat Dresden in Germany, and I'm going to lead you through the upcoming 20 minutes. Actually, when talking about disruptions, we are talking of this kind of severe events which are causing massive service deterioration, such as infrastructure failures, derailments, or even bad weather conditions. And unfortunately, they are heavily impacting our service, usually resulting in massive service deteriorations. And actually, they are impacting two groups of people. On one hand side, of course, quite obviously, our passengers, since they want to get from A to B, but also our dispatchers, since they are actually trying to keep our traffic on track or get it back on track. All right. And so we were wondering how we can actually get precise delay predictions for train dispatchers and passengers during disruptions. And for answering this question, in the upcoming 18 minutes, this is our schedule. So at first, I will give you a better understanding about the problem description, while then having a short look into theoretical background and model formulation, while then having a closer look into experiments and the results our proposed model was actually capable of, and finally drawing some conclusions. Let's start with the problem description. The first part of the problem is the railway system, right? So we are talking about prediction in railway system, and railways are often operated in networks. And since they are complex interconnected systems, they are usually heavily impacted by disruptions. And also because they are complex systems consisting of interconnected and highly dependent processes, they usually require a holistic view for capturing the entire impact of a disruption. Talking of delay prediction, we are actually more or less in the setting of time series prediction. So actually we aim for predicting disruptions of delays, DLS, in the railway system per line and station. And in best case, simultaneously for all lines and stations. So more formally, we are actually looking for a function which is actually to map a sequence of previous events in order to predict a certain amount of upcoming events. And we used an existing model and adapted an existing model in order to tackle this task, and this is what I'm going to show you now. So actually we were adapting the well-known and also successfully applied Lstm network for approaching this time series problem. Actually, Lstm network is a recurrent neural network which relies on a so-called internal state, which actually can store information over time, meaning over sequences of input data. And this information on this internal state can actually be explicitly controlled by the so-called gates. And we have like three gates: the input gate, the output gate, and the forget gate, which actually can control the information which is added to the internal state, which is taken from the internal state for performing a prediction, for example, and which is erased from the internal state over time. And we actually adapted this network to allow for a more holistic view, since actually here for the gates only a vector is processed by applying a function. We were changing this by applying these functions on entire graphs. So actually, instead of taking vectors, we were actually performing graph convolution here and applying the same activation functions for controlling the information flow. So actually now, instead of having vector representations, we actually have graph representations and can process sequences of graphs, hopefully allowing for this holistic view we're aiming for. Yes, And actually this all got applied in an encoder-decoder architecture, which has already been successfully applied in machine translation and agent-based prediction. And it consists of an encoder and decoder component. And the main feature is that it actually allows for a dynamic prediction horizon, which might be necessary when talking about the different temporal ranges of disruption impacts. And actually, we applied our GLSTM network within this encoder-decoder architecture in order to perform n sequence of graph predictions based on the previous m graph sequences. And actually, each component consisted of a modified GLSTM network, so we were able to perform this time series prediction, hopefully capturing the complex systemic characteristics by utilizing the corresponding network graph. This is actually how the process looked like, so to give you a better understanding. So actually you can see we are feeding in the encoder the sequence of input graphs into our GLSTM, and it stores information over time, finally being presented in this so-called encoded graph, which can then be used by the decoder as a starting point for performing predictions. And the predictions are actually getting fed back into the decoder as input for the next prediction stack, so the predictions build upon each other. And now, after giving you an idea about how our model works, we want to have an insight into the results we produced. But at first, for give you a better feeling about which data we used, I want to have a short part about data description and preparation, while then finally come looking into the results. So actually, the data we used was simulated data of a mesoscopic agent-based simulation model. We decided for a simulation data rather than real-life data because we didn't want to have hidden surprises. So we actually want to have full control over the input data, which is of course given by our simulation. Actually, we simulated railway operations of 5 hours, including random disruptions on network links, finally resulting in 5 disruptions with durations between 0 and 60 minutes. And also, railway traffic management measures were applied, such as replatforming and cancellations, in order to have a more realistically shaped railway operations. Here you can see an example for the data which was produced. So actually you can see the train paths from station 1 all the way up to station 8, and you can see the different lines and the corresponding train paths, and you can also see the effects of disruptions such as queuing or service irregularities resulting from certain disruptions. This data then was transformed into a graph-based representation. So actually stations were mapped to nodes and railway corridors were mapped to edges. And in general, all non-topological features such as train lines, infrastructure, occupation, and so on were transformed into graph-based features. So finally, we obtained like 3 different types of people, namely three different types of features, namely edge features, node features, and global features. And they were each consisting different information. So the edges, for example, were containing the max infrastructure speed, the infrastructure section length, but also occupation information, actual driven speed, line information, and scheduled times. Same holds for nodes. And then we also gave some global information, such as the total number of disruptions and the remaining disruption duration, since we wanted to prevent that the model aims for predicting disruption durations. Then we scaled the data down in order to use it to the model, and finally came for training the model. The model was trained based on 4,560 samples, each containing a time series of 900 time steps, and it was based on the loss function of the mean squared error using these hyperparameters. So being trained for 100 epochs, batch size of 3 with a initial learning rate for the Adam optimizer of 0.001, and a total number of 56 GLSTM cells per encoder or decoder component. And now let's have a look to the aggregated results. And for that, we actually calculated a metric over 1,650 randomly selected samples, and also benchmarked the model against the so-called naive model, where we just took the mean overall input time steps in order to get one prediction for all prediction time steps. And these are the results. And you can see that unfortunately our model performs even worse than this naive benchmark. In terms of mean forecast error, you can see that our model shows a slight overestimation tendency comparing the benchmark model. And regarding the mean squared error, so the overall deviations, you can see that the model performs even twice as bad as the benchmark model, which overall indicates a low performance level. Looking at exemplary results, we wanted to get detailed insights into the model's performance. So actually we chose 3 distinct scenarios, namely an undisrupted, a disrupted, and a recovering one, to see how the model performs under different states of railway operation. And for making this performance comparison, we applied a newly introduced metric, the so-called aggregated station delay, which is simply the sum over the delay of all lines at a certain station. And these are the results. So actually, we compared per scenario the results of the ground truth data and the prediction. And you can see for the undisrupted case, we have no delay in the ground truth. However, our model actually predicted some delays. Constant over time, it predicted delays of a certain magnitude of between like 0 and 10 minutes for different stations. Regarding the disrupted case, where actually disruption causes delays at station 4, we can see a different behavior. Our model actually nicely captures time points where some events occur, as well as the correct location, station 4. However, the magnitude of a delay, probably also resulting from the wrong initial predictions, was rather poor. Regarding the recovering setting, you can see that actually when the delay the disruption got cleared, the delay is actually vanishing at station 4 and increasing at the succeeding station 5. Our model again shows the performance as in the disrupted scenario, nicely capturing location and time point, but still magnitude-wise it is far off. Despite our poor predictive results, we still aimed for getting more insights about what is happening in the model. So actually we were aiming for more transparency and to get an idea about what is happening in the model. So actually we aimed for interpreting the internal states and the resulting model mechanisms, potentially allowing for deduction of captured or learned relations. And we analyzed 3 parts, namely the internal encoder memory, the representation which is then passed from the encoder to the decoder, and the decoder cell state, which is varying over the prediction horizon. In this presentation, I will dive deeper into the decoder cell state, which is to follow next. Yeah, so the decoder cell states are basically dynamically changing over the entire prediction procedure, in our terms at most 450 time steps. And since it's dynamically changing, we needed to find a measure which is actually capturing this dynamics, and we finally ended up using the coefficient of correlations per internal dimension for the individual graph parts. And since our predictive performance was rather poor and the decoder iteratively is using previous predictions, we decided to base this analysis on the ground truth data in order to get a feeling about how the decoder performs on correct data. And we again use the same exemplaric scenarios to assess this behavior. Actually, as an example, I'm giving you the heat maps for dimension 2. Heat map is showing actually for different parts of the network, namely all links and all nodes, the coefficient of correlation and showing indicating a positive correlation in red and the negative correlation in blue. And you can see that there's a nice distinction between the network's components, where you can see that there is a strong positive correlation between the nodes and the links respectively. However, there is a clear distinction between the nodes 1 and 2 and the remaining network, since they are kind of the start or the source nodes of our network and thus somehow different. And regarding all other parts, the clusters are nicely separated by showing highly negative correlations. So you can see, in general, we can distinguish between nodes and links. In the disrupted case, you can see that there is something massively changing. So you can see that actually, when a disruption occurs between station 3 and 4 on link 3, that there's something changing. So for example, the succeeding station of the link shows significant deviations in correlation. So actually there's increasing correlation in the succeeding links of the network and a decreasing correlation with the following nodes. The same holds for the disrupted link, where actually the correlation among the network's links drops and the correlation between the link and the network nodes, the follow-up nodes, increases slightly. What you can also see is that there is a decreasing correlation between the links 1 and 2 and the links 5 and 6. So actually a decreasing correlation between the follow-up links and the links before the disruption. We can also see that this behavior, of course, separates the network somehow in the links which are following the disruption and the ones before in general. Talking about the recovering phase, so actually the disruption got cleared, we can see that this behavior actually propagates through the network. So we can actually see that now slowly the correlation changes happen at station 5, which is a follow-up station of station 4, and also on link 4, which is the corresponding link. We can also see furthermore that the network gets even more segregated in terms of nodes, but also links. So now we have a cluster of links, which is the link to station the link 9, the cluster of links 7 and 8, and the cluster of links link 6. So actually we can see that this kind of reproduces the behavior of how we would the disruption impact, how we would expect the disruption impact to propagate through the network. So actually this dimension shows a kind of local behavior and takes a rather element-wise perspective. So for concluding the talk, Thank you for your attention up until now. These are my sources, and I'd be very happy to answer all of your questions.